Okay, welcome to chapter 6 of this plasma physics course. We're going to talk about average values and macroscopic variables. We're going to use the elements defined in chapter 5, those variables, to compute some averages, which will be the basis for the development of the theory of two fluids and MHD equations. They will all be based on the values that we are going to compute. So since we have defined a phase space in chapter 5, now we're going to compute the averages in volumes in this phase space. So the mean value of some property, let's say chi, at the position R of our phase space, and velocity v at time t. This is some property that we want to compute the averages. Okay, and remembering that we have defined this quantity which is the number of alpha particles in a volume. So this is the number of alpha particles inside this volume element at position R and V. So from equation 3.1 of chapter 5, you will remember that we have defined this quantity to be function of f, the distribution function at the same position and time, times the volume element. So this was defined in chapter 5, and if we multiply both sides of this equation by chi, we end up with this. So RV T times d6 and alpha RVT. This will be equal to the other side. Doing the same here. Now this is equation 1.1. This quantity here now is the total value of chi for all alpha particles in the volume, right? So I have the number of particles times this quantity, so I have the whole total value of chi for the element. The value of chi in the d3r independently of v is the integral of the right hand side. So if I want to know the value, the total value of of chi, independent of v, so I'll have to integrate this in the v space. So I want to know only as a function of space and not as a function of velocity. So integrating that, I end up with this. Integrating the right hand side in V, you have, so this is going to be integral in V, so I can remove dr from there. It's not a function of velocity. I'll integrate in V, and this will be the quantity. Now, from chapter 5, we know that n, minor n, small n, this quantity is the total particles, total number of particles inside this space volume, right? Total alpha particles in D3R, independent of velocity. Then if you want to compute the mean value of chi in the space of the velocity space for alpha particles, then all you have to do is to divide 1.2 by this quantity. All right, so you have the mean. And the mean value we'll denote by this. So we have bracket chi RVT, and this for each alpha particle. So I have, well, I will divide by n times dr3, right? Sorry, d3r. Then in this case, I will cut with this d here and end up with this quantity. Chi RVT times F alpha V T. Okay. So this is basically the way we compute the averages in this chapter. We have done something like this in the previous chapter, but this is just to set that for the current chapter. This is going to be our rule of thumb to compute the averages. So I have the integral of this quantity related to this distribution of particles integrated in V. So it's an average in relation to the velocity. So let's start computing some averages then. Let's use some values for chi. So chi is a generic variable that could be anything. So let's start with a few examples. Average velocity. And peculiar velocity. So we're going to compute this average using chi equal to V in 1.3. So, and we're going to call this average U. So U is the mean value for the velocity of alpha particles at this position, at the volume element at this position. And we can use also this notation. So this is just add V in place of chi in this 1.3 equation, and we have this. This is one of the most important averages that we are going to use. So let's take note of it here. This is 2.1. Remember that R, V, and T are our independent variables in this context. And if chi does not depend on V, we have the average. Well, let me. If for some reason you're computing the average of some quantity that does not depend on V, then we can write it like this. If chi does not depend on V, then we have the average of this quantity. It's just a function of R and T in this case. For alpha particles, it's just the quantity itself. You don't need to use the brackets in this case. Why not? well, because it does the average being computed on V space, right? So like if you I'm gonna do it for you in place of chi so that you can realize that this is true. So if you have the mean velocity, but u is not a function of v, so because u is the average velocity, so there's no point in saying that it's a function of velocity. It's a function of space, position and time. So it's computed like this. So this is the expression for the average of the average velocity. That's what it's being computed here. So it's just a silly way to do it, because if it's an average, why are you computing the average of the average? But if you add the average here in this equation, you end up with this. You have, well, this is not a function of v, so you can take it out of the integral. And then there's just the integral of the distribution function, d3v. Oops, no space here. d3v. Okay, and these are arrows, vector quantities, right? And well, this is just n. N is actually the integral of the distribution function. So we end up with this. I didn't have to do this, but anyway, in case you didn't see it, now you see it. It's, of course. So there we go. So you have it. The average of the average is the average itself, of course. But this is important because it will simplify a few equations in this chapter. So it's good to have it established. Regarding the notation, we may write it then like this, which is silly, but we may also just say this because we have shown that it is like this, or you may write it like this. You may not use the alpha here if it's redundant, if it's obvious that you're computing it for each alpha particles, then you don't have to use it. Okay, sometimes they're just going to use it like this, or sometimes like this, or this. Okay, there is a fluctuation or random velocity. Random velocity, which is defined as, let's use c for this. It's the velocity, the particle velocity minus the average velocity. So that's also called the fluctuation velocity. Fluctuation, sorry. Fluctuation velocity. So it's just the velocity minus the average of the alpha particles. So you see that if you compute the average of the fluctuation velocity, you will have the average of v minus the average of u. You see that here I have used v, the alpha index, but here I'm not going to use the alpha because it's already obvious that I'm computing the alpha index, so I don't have to use it here. So, but this, what is it? I have used it like here. Where is it? Here. So this is equal to u alpha, right? So it's just like this. And this is like this. So the mean fluctuation is always null. It's always 0, right? Okay, I used 2.1 here. Okay, we will also need the concept of flux. What is a flux? The flux of a quantity chi is defined as this: the quantity transported through a surface per unit area and unit time. So let's write it. Flux of chi is the amount of chi transported by the particles, because each particle has some amount of this quantity, and if the particle is moving, it goes across some surface and it's transported through a surface. Per unit time, per unit area and unit time. Okay, that's the flux. We'll use then a surface element. Let's say we have a surface element here. So it has a boundary or a border here. And it has a normal vector, unit normal vector. This is a ds element of a surface. And we will need to define what is the positive sense for this surface. We'll orient the surfaces. And usually we're going to use the anti-clockwise direction for the boundary. So if you define the anti-clockwise as your positive direction, then the upper normal will be the positive direction. Okay, so we have two sides of the surface. You have this side pointing upward and the other side pointing downward. So downward in this case would be negative, because this is important because we want to compute the flux, and the flux will be a positive or negative quantity depending on whether you have most particles going this way or this way. So we're going to use anti-clockwise as a positive direction usually, and the upper normal in this case to be your positive direction. If you have a closed surface, then there's no problem. You have the outward normal will be the positive. Okay? This is the positive. If the surface is closed, sorry, this should be unit normal, right? So if you have a closed surface, this is a surface. How can I show this is a surface? Let's do it like this. Okay, so if you have a closed surface, outward normal will be, it will define your positive direction. And if you have an open surface, then counterclockwise direction for the boundary, and the upper normal will be the positive direction. Now, in order to compute the flux, I need to draw a prism. So this image, this prism, will illustrate the motion of particles with the velocity vector v. You could actually consider v plus dv, the velocity of particles. So we have a bunch of particles with this velocity vector given by v, or v plus some small deviation dv. And then we have a surface here, ds. ds is the surface element, and it represents the area of the surface element. The surface element may be given by its area, ds, or by its vector element, ds arrow, which is just the normal, unit normal, n times the area ds. So Sometimes I'll use ds with arrow, sometimes ds without the arrow. The without the arrow is just the area. So this is the element, this is the velocity, this is the normal, and the prism represents the motion of the particles in this region through dt time units. So in dt time units, if they are moving at the velocity v, they will cover this space, right? So we have here x, y, and z components, and these particles are inside this prism, and the volume of the prism, prism volume, is just area of the base, times height, right? Area of the base is ds. What is the height? Well, the height is just v dt projected in, on the normal, right? So this projection will be this height. The height is actually the v dt projected on this direction. The dot product here represents that projection, right? So the volume, let's call the volume just d3r. That's the space of this volume. It's the area of the base, ds, times the height. Height is n dot v dt, right? But n ds is arrow ds, right? You may write it like this, v dt. One way or the other. So we may now compute the total number of particles inside the prism with velocities between v and v plus dv. And this total number is f, the distribution. I need to know, always we're going to compute quantities based on the distribution. This is the number of alpha particles inside the element per unit volume and times dr, this one, right? So this is, well, I can use now this definition in place of here. This is n v dt ds dv. Okay, I'm using 3.2, and this is 3.3. So the total quantity of chi property transported by these particles through the element ds in the interval dt is just 3.3 times chi integrated in v. So you may just do it like this. I'll multiply it, integrate in v, multiply by chi. So this is the amount of particles of chi transported by this by all particles inside this prism going through the area ds element. If you have n dot v larger than 0, then the particles will increase the flow. Increase the flow. If it's less than 0, then particles decrease the total flow that you're going to compute. The net amount of chi property per unit area and per unit of time will give the flow in the direction n. So we may compute this flow by taking 3.4 and dividing by dt and ds. So let's finally define the flow. The flow for us will be the flow of alpha particles through the in the n direction through the surface for a chi property of your particles will be given by 3.4 divided by dt ds. So it's just like this. Okay, by 1.3 you can write it like this. 1.3 is here, right? Where is it? 1.3, how? Go on. Okay, so I can just use, I have this quantity here, so I'll multiply it by here, and then I end up with this, n alpha r t times chi. Times n v. Well, let's use this shorter notation here, n alpha chi v n alpha. This is 3.6. So Vn will be this, okay? This we'll call Vn. It's not a vector, so no arrow here. Now, if you compute this quantity for the fluctuation velocity, no, actually, let's just substitute V by using V equal to C alpha plus U alpha, right? I have defined this previously. Using this in 3.6, then we have alpha n chi will be n alpha chi Vn alpha, which is, well, in place of V, I have two quantities now, chi C alpha plus U alpha. Now this is n component and alpha, so is this sum. This is actually an index, so which is the normal component of this quantity, and this is 3.7. Okay, remembering that this is this, and this is this. So we have already defined two expressions for the flow. The flow will be a one of the main quantities in this chapter, also together with the mean velocity. If you're moving in a frame with the velocity, the mean velocity of the flow of the particles, then this is 0 and you have only this. For the fluctuation, the flow of the fluctuation variables, this is also important. In a frame moving with velocity u alpha, then 3.7 becomes phi alpha n of chi now will be this only. This is the fluctuation velocity only. Well, there's another quantity that is worth mentioning, which is the particle, let's put it white, which is the particle current density. Particle current density. Or sometimes called particle flux. It is the number of particles passing through a surface per unit area and per unit time. So you can define it just by using chi equal to 1 and 3.6. We use here chi equal to 1. Then we get, let's use this notation for it. It's a gamma alpha n at position r time t, not a function of velocity because we're integrating in velocity field. So it's given by this. Now, if you use 2.1 from 2.1, where is it? It's far away. Okay, here. So we can, instead of writing this way, we can use this notation. So let's do it. Sometimes it's clearer to use it like this. Okay, that's 2.1. Now, if your average velocity is 0, so you don't have a mean velocity, then it's interesting to consider the flux of fluctuations only the fluctuation velocity. And in this case, usually we compute only the flux in a given direction, like the positive direction, for instance. Because if you have an oscillation and you have a surface, you're going up and down on the surface. So we consider just the up direction, for instance. So if this is the case, then this is a more interesting quantity to be computed. We'll integrate in V, but only considering positive V, that is the direction where you have, this is basically this direction. You have a fluctuation velocity dot product with the normal of the surface. This has to be larger than 0. Okay, so the integral will only consider those particles that with those velocities. So and here we just reproduce the previous formula, but with, okay, this is here, right? 3.5. Okay, we're using 3.5 with chi equal to 1 and V equal to C alpha. So this is the equation. is 3.5 with chi equal to 1 and v equal to c. Okay, so that is the flow of the fluctuation flow. We also have the max flow of the fluctuation. Let me draw it here. Let's write it here. M, just M plus this equation, this quantity gamma plus is the fluctuation flow mass, or mass flow, right? Yeah, mass flow. Okay, that's it for scalar quantities. Let's think about the tensor quantities now. This is more interesting and also more intricate, more complex to understand, so I'll try to make it as simple as possible. This is section 5 in this chapter in the book. So let's talk about the momentum flow. Diode. Diode is a second-order tensor. Okay, so most of you may be familiar with tensors, but some of you may not. So I think before defining the momentum flux mathematically, I think I'll give you a brief introduction about tensors, or how this tensor works. So it's actually something easy to compute. Let me think. Let's start with 3.6 maybe. Okay, we'll use 3.6, but now we're thinking about momentum, and momentum is a vector quantity, not scalar quantity. Then let's do it. Let's use 3.6 with chi equal to a component of the momentum of particle alpha. So since momentum is a vector for each particle, we'll write this equation for each component of this vector. Then we'll have component by component, and I can define a vector of a flow vector, okay? So doing this, let's start with the mathematics, then I'll comment on the tensors later. So using 3.6 with, even worse, with chi equal to the J component of the alpha particle momentum. So we get, well, what is the J component of the momentum? It's m alpha, the mass of the alpha particle, times the velocity of the particle dot j, the j direction. So this is going to extract the j component of the velocity. So I can write it like this. Okay. All right, then we'll define the momentum flow diode component. So this is for alpha particle in the j. This is the j component of the momentum. In what direction? In the n direction. N is the direction of a normal direction. So we'll have a flow volume. And we'll consider three normal directions, right? So These are the directions. I have the direction of x, z, and y. And this will be the component of a vector. Like I have, let me change the color here. So I have vectors like this. This is a momentum vector in the z direction. So this vector has three components because you can decompose it in three directions here, right? You have x, you have y, and you have z on this surface, and you have the same in different surfaces. So you do have a y component for this, a x component, and z component. So we will be able to compute all of them now. So you have here, all right, and you may project it onto this normal direction, and here you would have the alpha y y. Usually we don't use the hat here, just the letter. So this is gamma alpha y y, which is the component of this vector flow gamma alpha in the direction y. You have y direction, you may compute the x component and the z component as well. So you have, for each plane here, you have a vector, and this vector can be decomposed into three components, all right? This is not immediately clear when you read the book, so I think thinking about this drawing might help you. So what is the expression for alpha j, gamma alpha jn? We'll use it like this. So 3.6, right? So you get 3.6, and in place of chi, I will use a momentum. And in place of Vn, I'll write it like this, n dot v. We get, well, we can write in both ways. Let's just make it explicit here. So the expression, it goes like this. V dot j. J will be either x, y, or z. So here I'm just using generic j. And then the normal v. So this will be the normal direction, and j will be these small components which I am decomposing the vector. So we have two indexes here. And this may be written like this as well. Vj, Vn. So this is 5.2. And well, so this is just m times m, right? For particle alpha. It's the mass density for particle alpha. But now, we have seen that V can be written like this. But V has a fluctuation component plus a mean component, right? Then I can write alpha jn as this. We'll just expand this v here into c plus u. C alpha plus u alpha, j component times c alpha plus u alpha, n component, and we are interested in the average value. Okay, I will just distribute this product here, so we get rho m alpha times the average of C alpha j, C alpha n plus C alpha j, U alpha n plus U alpha j, C alpha n plus U alpha j, U alpha n. Now we can group these quantities. This average can be written like a sum of small averages. So this is the average of this couple here plus the second one. These are just properties of these average operations. You can decompose it like this. Plus, it makes life easier for us. Okay, now there's one important thing here. These two quantities are zero. Why? I'll show you in a minute. So for now, just consider that these are zero. I'll just show it later. But now we end up with just these two quantities. So we have m times alpha j, C alpha n plus the density. Oh, sorry, this is not E. It's alpha. U alpha j, U alpha n. Okay, now this average here, we can use 2.2 to write it like, let me see, 2.2, where are you? 2.2, 2.1, 2.2. So I don't need the brackets when the quantity is, you can either use the bracket here with the alpha or like this, okay? If chi does not depend on v. Since u does not depend on v, I can write it just like this, right? So let's do it. This ends up like this. C has to keep the brackets, but for u, I just write it like this. So here I use 2.2, and this is 5.3. Now, let's show why these two quantities are zero. Observation. Let's write C alpha j times U alpha n. This is the first, where is it here? The first one is this. So by definition, this is 1 over n alpha RT times the integral in V of C alpha j U alpha n, RJ, right? Sorry, RT. Times the distribution function f RVT d3v. Okay, now C is the fluctuation velocity. Fluctuation velocity may be written like this. Integral V of Vj minus U alpha j, right? So this is the j component of the velocity and the u component minus the j component of the mean velocity. Okay, this times this, alpha n f alpha d3v, right? And this Okay, well, this is not a function of v. I can remove it from the integral. U alpha n over n alpha rt times the integral in v of this quantity. What now? Let me just split this integral into two parts. So this is u alpha n times 1 over alpha, the integral of vj f alpha d3v minus 1 over n alpha v u alpha j f alpha d3v. Okay, and this will give us, this is just by 2.1 is the definition of this quantity. U alpha j. And this by 2.2 is just the definition of U alpha j. So this is 0. Okay. Using 2.1 and 2.2. Okay, you can check it. And the same for U alpha j C alpha n. Okay. Because in 2.2, just to make sure, let's see, yeah, this is 2.2, but after 2.2 you see that this is given by this here. So we have 1 over n, integral of u alpha times the f. So this is actually, this quantity is this, and can be written like this. The only difference is that I added a j component here. Okay, so that's correct. We have it like here. Okay, this is by here, and this is by definition u. All right, so we have the expression for each component of the flow diet. So this is a second order tensor, and the components are given by 5.3. What does the full tensor look like? We may have, from this expression, we may have alpha z, alpha y, and let's add alpha, you may have something like this, right? Alpha x. So I have 3 vectors, each one of them with 3 components given by an expression like this, okay? Is that it? Yep. Then you have this component equal to, sorry, this vector with 3 components, alpha xx, alpha yx, and alpha zx. You have alpha y given by alpha xy, alpha yy, alpha zy. Don't be confused with the notation. Here it's alpha y, but here in the components, the individual components of this vector come in the middle of it, not in the end. So this may be confusing, but remember, the final one is indicates which is the normal direction, normal to the plane you're computing it. Okay, so this is like this, and the same for the z direction. alpha y z, alpha z z. This is the tensor. If you put each one of these vectors into a column, you will have this matrix or this tensor, right? You have it like this. This is the flow, momentum flow tensor. Now there are different notations for this tensor. This is perhaps the simplest one. It makes clear that each column is a vector. But there are other notations, and I will give them to you, because otherwise you may be confused. Sometimes they write it like this. Sometimes they do it like this. X, X. Each component is given explicitly, and you have X, Y. This is confusing for me, I don't like it, but I'm just putting it here for you to know. Plus yx, yx plus yy, alpha yy, yz, alpha yz, and the final line alpha zx, zy, zz. And well, each of these vectors is like this. So you have 1, 0, 0. You have y equal to 0, 1, 0. You have z equal to 0, 0, 1. Then, if you do it like this, this pair of vector values here is a tensor product. So x is the tensor product. Like xx is x. Maybe you know all this, you have seen it in a different subject, but no problem. It doesn't hurt to see it again. So in order to compute this product, you write this first vector as a column vector, and the second one like a transpose of the vector. So it's like this. So this product will be actually a matrix. You compute it like a matrix product here. Okay, then xy will be this, and so forth. Sometimes you may write the same thing like this. Gamma alpha will be this tensor here, composed of these three vectors, times this, oh boy, I'll write it all again. Let's do it. Alpha xy, alpha xz, alpha yx, alpha yy, alpha yz, alpha zx, alpha zy, alpha zz, times this, just to make things more complicated. Why not? Yeah, that's it. all the thing, all these notations denote the same thing. It's just the tensor. So the easiest way to do it is just to write the matrix. Okay, 5.4 is the preferred way for me. Okay, but you may use anyone. Now from 5.2, let's see 5.2 here. You see that alpha Jm is like this, Vj Vn. So it's the same as alpha Nj, right? You just switch the vectors here. So this matrix is actually symmetric. Okay. From 5.2, alpha Jn is equal to, hey, sorry, this is not H, it's gamma, right? I'm writing it wrong. Yeah, not H, sorry, this is not H. It's gamma. Actually, not gamma. What letter is this? This is a capital pi, right? I'm saying gamma. It's not a gamma. It's a capital pi. Okay, capital pi alpha Jn is equal to capital pi alpha Nj, right? Then this matrix is symmetric matrix. That is, you have this, right? Equal to its transpose. Thus, only 6 of the 9 components may be computed. They are independent. Using the dyadic notation for 5.3, let me see, where is 5.3? Okay, 5.3, each component, may be written. Since you know the components of the matrix or the tensor, you may write the tensor using this notation. Alternative notation. One more. Based on 5.3, you know that alpha RT will be given by rho m alpha times C alpha plus U alpha. Okay, based on 5.3. Now let's introduce another tensor, the pressure tensor or pressure dyad. This is section 6, the pressure dyad or second order tensor. Well, what is a pressure? A gas pressure is the force per unit area done by the gas molecules through collisions with the walls of a box. Okay, so you have a gas inside a box, and the particles are colliding with the walls of this box, and this will give you the pressure. So this is equal to the rate of transfer of momentum, of molecular momentum to the walls. If the surfaces are moving, so suppose you have a surface, and this surface is moving with the mean velocity. Then in this case, the pressure will be the rate of transport of molecular momentum per unit area, and the flow of momentum will be due to motions or random motions of the particles. Because you know the particles have the mean velocity plus the motion. So if the surface is moving with the mean particle velocity, then the only thing that remains is the fluctuation velocities. All right. So let's write the definitions of the pressure for this case. Using 3.8, I'll use 3.8, which is, let's go back, Okay, here. 3.8, the flow is like this, but we'll use, in place of chi, the jth component of the momentum due to fluctuation only. So, since you're going to use only the fluctuation velocity, I will use this definition of the flow, but of momentum flow, but only for the fluctuation. So this part will be 0. So this is what we want. Oops, I did something wrong here. Where is it? Okay. So using 5.3 with chi, the jth component, of momentum due to fluctuations only, we get P alpha Jn equal to rho m alpha C alpha J C alpha N. So we have defined our pressure diet. Or if you use 5.6 here, this notation for the whole tensor, we don't have this part, so, or using 5.6, P alpha is equal to rho m alpha C alpha C alpha. And from the same 5.6, I can write, well, I don't have this, but if you want, you may use this, which is the whole thing, minus this quantity. It may be useful to write it like this, P alpha in terms of the full momentum flow tensor. I just removed this part from the tensor to get the pressure. Another quantity is force per unit area. This is useful as well. Well, suppose we have a surface. This is a closed surface in the plasma. So we have a closed surface. We have some surface element, ds, with the normal. Just let me draw it like this for you to know that it's a closed surface. And so ds is the normal times the area of the element. And the normal for us will always be the outer normal. And we'll have a force, F. This is the force per unit area due to random motions of the particles. Do not confuse this with the F alpha of the probability distribution. That does not have the arrow. If I put an arrow, it's the force, not the distribution, all right? So this is defined as minus the pressure tensor times the normal, which may be written like this. The normal component of the velocity from this. Okay. . if n coincides with one of the x, y, or z versors, then you have this operation selecting the one of the three columns of the P tensor, all right? Now you may be asking, why the minus here in this formula? Why the minus? Let me try to show you. Why the negative sign in 6.4? Well, suppose you have, oh sorry, this is Portuguese. Suppose you have C alpha dot n larger than 0. What is this situation? You have your area element, ds. You have your normal, n, right? Then you have c, the fluctuation velocity vector. If you have c dot n larger than 0, it means that the angle between c and n is smaller than 90 degrees, right? This is the angle. I shouldn't use alpha, right? Because alpha is the index of the particles, alpha particles. Let's say gamma. Okay, then gamma is smaller than 90 degrees, right? In this case, the particle is going outward from the closed surface, and it's transporting the fluctuation momentum outward. So the momentum is decreasing inside the volume, right? Inside S is decreasing. Okay, if C alpha dot n is smaller than 0, then you have the angle between C and n larger than 90 degrees. So if it's larger than 90 degrees, then it has to be pointing downward in relation to this surface, right? In this case, momentum is being transported from out to inward, right? Because the arrow is pointing in this way. Momentum in S is increasing. Okay, so that's why we have chosen to use the negative sign. This minus n alpha C alpha dot n, this quantity times the S. That's just like this, right? I just multiplied Pn by ds element, the area, is the rate of change of momentum. Sorry, momentum, not momentum. Of momentum in S. Due to particles that cross ds. Okay, all right. Now, just for you to see that this operation just selects one of the columns of this tensor. Let me give you an example. So if n is equal to x, we have minus p alpha dot n, right? So this is, let me write it like this also. It's given by, how do I compute this? I have the whole tensor here. P alpha xx, I'll write the full tensor. P alpha yx, P alpha zx, P alpha xy, P alpha yy, P alpha zy, P alpha xz, P alpha yz, P alpha zz. Okay, this is P alpha, this is minus, right? Minus this. Dot n, if n is x, x is just 1, 0, 0, right? So in this case, you have the scalar product of this quantity with all these, with this vector, right? For each column, this is a dot product. Since this is a matrix, a dot product must be computed for each line. So each line is a vector, and it'll have minus P alpha xx minus P alpha yx and P alpha zx, right? This with this is this, this with this is this, this with this is this. All right? So I have just selected the first column. If I use Y, you will select the second. Z, I'll select the third column. Okay? Now, if I draw the, let me try to draw it here, the surface element. I have the S here. I have, suppose this is x direction. Then, if I have the pressure in this way, P alpha x, because it's in relation to this. So P alpha x is this. It's a vector with 3 components. And I may write the first component is like here, right? This is, oh, let's see. This is P alpha xx. Then you have the other two. You have, maybe it's like this. This is z, and this is y. Then you have 2 tangential directions and 1 normal direction. Use a different color for the tangential component. So this will be a P alpha zx, and this will be the P alpha yx, right? The z and y components of P alpha. Then we have P alpha xx normal to ds, and I have P alpha yx and P alpha zx. These are the tangential pressures. Tangential is with T or with C in English, I don't remember. Well, you correct me if it's wrong. I think it's T, right? Tangential. Oh boy, whatever. Tangential due to shear forces. Sorry, tangential pressure, right? Tangential pressure due to shear forces. So here I have shear, here you have the normal direction. All right. Okay, now there's an interesting result related to this. Let's think about force per unit volume. Now, from 6.4, let's check it. 6.4 is here. Okay, so we have a force, and let's think of this force in this case and integrate this in a closed surface like this one. From 6.4, we know that F alpha is minus P alpha dot N. Okay, I'll integrate this along a closed surface S on both sides. So integrate this side, integrate the other side. Okay, but here what we have the flow of this pressure across a closed surface S. We can use the theorem of the divergence here, also called the Gauss theorem, to compute this surface integral in terms of the integral, the volume integral of the divergence of P. Okay, so by Gauss theorem, we know that this integral in the surface is equal to the integral inside the surface in the volume V of the divergence of P. This is Gauss theorem. All right. Now, if I just divide both sides by volume V, I get the following: 1 over V of the integral of F. And the same in the other side. This is minus, right? Minus 1 over V, volume divergence of P. Now, if you take the volume, the limit of this internal volume going to 0, then you have this. Minus a limit of V going to 0 of 1 over V, V divergence of P. Now this part is approximately equal to minus the divergence of P, 1 over V of D3R. Why could I take the divergence of P out of this integral? Is it fair to think that the P is not a function of position? Well, since the volume is very small, if divergence of P is a continuous function in V, then the value of divergence of V will not vary very much, will not change very much in V, because V is very small. So we can take it, suppose it is constant, with the divergence being the value of the divergence in the middle of the surface. Okay, so you had a, so this is awkward. So we had a volume V, and you have a central point here. You're computing the divergence of P. But since this is shrinking, I'm taking the limit of the volume going to 0. This is going to shrink towards a single point. So I'm taking this approximation that the divergence is approximately the divergence of the central point. It's about the same in all points in this small circle, small sphere actually. Okay? So that's why I could remove it from the integral. Well, it's not very, I mean, it's not mathematically precise, but it's physically acceptable. So, supposing that this is continuous in V, then for small v, we can use divergence of P approximately equal to the divergence of P at the central. Center of V. Okay, fair enough. We have this approximation, and this integral in d square v r is just v, right? I'm integrating in space, so this is actually the volume 1 over v times v. Okay. Therefore, the limit of v going to 0 of 1 over v of integral in s of f ds is approximately equal to minus the divergence of p. So our conclusion here is that minus the divergence of P is actually the force, this force F, over a unit volume, because I have here dividing by the volume, so per unit volume, due to random motions of particles. And this minus P dot m is the force per unit area of the surface. So this for the surface, this for the volume. Let's talk now about scalar pressure, because we have talked about the vector and tensor pressure. Now let's think about scalar pressure and absolute temperature. Well, what's the definition of the scalar pressure? Scalar pressure is just 1 over 3 times the trace of the pressure tensor. So the trace will be just the sum of the elements of the main diagonal of the tensor. This is it. Or you may write it like this. If you use 6.1, by 6.1. Okay, this is going to be equation 6.9. The absolute temperature is the kinetic energy, the mean kinetic energy associated with random motions. So you have it for each direction. Let's write it like this. This K is Boltzmann's constant. You have the temperature of alpha particle in the I direction. It's going to be half this quantity here. Okay, just a random direction in the component I for this 6.10. I could be either X, Y, or Z, and K is Boltzmann constant. If you have an isotropic distribution of velocities, then for isotropic velocity, then you have C alpha square equals to, in the direction X, is equal to direction Y and direction Z. So we could just say C alpha instead of anything else over 3. Here C alpha is just the sum of the components square. In this case, you can write for the pressure, you can substitute this for this, and you get P alpha equal to 1 over 3 rho m 3 C alpha square, or simply rho m alpha C alpha square. Now, if we use 6.11 into 6.10, let's rewrite this in terms of temperature, in terms of pressure. What is the relation? So using 6.11 and 6.10, we get 1/2 k T alpha equals 1/2 m alpha P alpha over rho m alpha, which is equal to 1 over 2 m alpha B alpha. And this is the mass density, right? So it gets like this. And we end up with this famous relation between pressure and temperature. This is the state equation for an ideal gas. Well, I think I'll change the notation a little bit because this may be confusing. My capital P's are looking like the small p. So this is actually a small p. Do not confuse it. Capital P is the pressure tensor. This is not a tensor. This is just the sum of the main diagonal elements, right? So this is, let's try to make this more like a small p. This is small p. Okay. Small p, this is also small p. Sorry for this. Okay, this is small. All right, then for isotropic distributions, the p, let's write as an observation. For isotropic distributions of velocities, P, now capital P, is a tensor, it's a diagonal tensor. With all elements equal to this P alpha. So in this case, you can show that minus the divergence of this tensor is equal to minus the gradient of P alpha field. When you don't have viscosity or shear, then P is always diagonal. But it may be anisotropies if the elements in the diagonal are distinct. So you don't know if you have equal elements in the diagonal, but it will be diagonal. The next vector that we can define here is the heat flow vector. We have defined the flow, the momentum flow tensor. And now we can define, we can define the heat flow vector. Well, the flow of thermal energy or random energy through the surface with normal n is obtained by using chi equal to m alpha C alpha square over 2 in 3.8. I'll not show this equation here because it's too far away in the slides, but you can check it out. Then if you do it like this, you end up with the following expression. Q alpha n is equal to n alpha times this C alpha square over 2 C alpha n. And this, well, m is just the mass density. I can write it like this. And the rest is here. C alpha square C alpha. This is the n component. Well, this is actually a unit vector, right? So hat. And this is equal to the Q alpha dot n, where Q is a vector defined as Q alpha is equal to 1/2 rho m alpha, fluctuation velocity like this. This is the heat flow vector. Might be useful for you. Now let's talk about third order tensors now. And one example of a third order tensor is a heat flow triad. defined like this: Q alpha is equal to rho M alpha, C alpha, C alpha, C alpha. Triple product of alpha here. Now, what is a triad or a third order tensor? Well, zero order tensors are scalars, right? So if you have a scalar quantity, you have a zero order tensor. Or order one tensor. Order one tensors are vectors. Order 2, we have shown the pressure. Order 2 tensors are matrices. And what are order 3 tensors? What is this structure? How do I draw this structure? Well, we can think of it in terms of a cube, like the magic cube. You know, that one with the different colors on each side that you try to match, and it's impossible to solve. Kids like to do it. Well, the magic cube, let's try to draw it. What are the components of this? Okay, this is the tensor, right? The components are actually like this. You have Q alpha, index y, I, j, k is this. C alpha I, C alpha j, C alpha k. So this is order 3 tensor. You have a set of rows indexed by I. You have a set of columns indexed by J, like if you say Q alpha I j k, right? And then you have a set of, they call pages, indexed by K. So each one of these pages is a page. So you have the first page here, the second page here, and the third page here. In this case, we have 3 pages with 9 components each, right? Yeah. With a total of 27 components. That's how many you have in this tensor. You may write Q like this. Q alpha x in the direction x plus Q alpha y in the direction y plus Q alpha z in the direction z, with Q alpha n equal to each one of these pages. Alpha x, x, n, Q alpha x, y, n, Q alpha x, z, n, y, x, n, alpha y, y, n, y, z, n, alpha z, x, n, alpha z, y, n, Q alpha z, z, n. I think that is correct. If I didn't miss up anything, no, I think this is it. These are the components of each page. Now, equation 7.1, sorry, my voice is going up. So, 7.1, let's think about 7.1. If you want to write heat flow vector, you may do it like this. So it's actually C alpha square times C alpha n, right? So C alpha square is just, where is it? Oh, C alpha square, I have written it like somewhere here. C alpha square, I can use this. So let's rewrite it, the heat flow vector here. Oh, it's empty. No more pages for me. Sorry, my Jamboard is over. I cannot add more than 20 pages. I'll have to start a new document here. So let's do it. New document. So I go back. I have, okay, this is fine. Go back to Jamboards. Start a new Jamboard. Okay. Back to the heat flow vector. 7.1 can be written as Q alpha n is equal to 1 over 2 alpha times this C alpha x square, C alpha y square, C alpha z square times C alpha n. This is just C alpha square, and this is just C alpha dot n. Then we get 1 over 2 rho m alpha, and we can just do the multiplication here to obtain C alpha square, C alpha n plus C alpha y square, C alpha n plus C alpha z square, C alpha n. When you compare this with 8.2, let's compare 8.5 with, oh boy, it's in the different file. So comparing with 8.2, I cannot show it to you now. Comparing with 8.2, you will get Q alpha n equal to 1/2 of Q alpha xxn plus Q alpha yyn plus Q alpha zzn. Okay, just a different way to write the heat flow vector. Now, to finish this chapter, let's just write another triad. It is the total energy triad. Another third order tensor. It's defined by this rho ma times v. It looks like Q, the heat flow tensor, but it does not include the U component. It has just the fluctuation components and the velocity. So with component E alpha ijk equal to rho alpha vi, this should be I, vi, vj, vk. And this can be written like this. I Vj Vk times the distribution function d3v. Well, that's it. I think you have enough material to do the following lists. And I hope you have enjoyed our tenses chapter. See you next time.